हेलो एंड वेलकम एवरीवन। स्वागत है आप सभी का। एंड टुडे वी आर गोइंग टू डिस्कस ऑन टाइम डिपेंडेंट लॉसेस. So we were discussing pre-stress loss, which is broadly categorized into two categories. One is the short-term immediate loss and other is the long-term time-dependent delayed losses. So these time-dependent losses are the loss of pre-stress in the tendons. Due to what? Due to two factors. One is the creep and shrinkage in concrete, and other is the relaxation in steel. Let's just begin with the creep in concrete. So, creep is a time dependent increase of deformation, time dependent deformation. Under sustained loading, here we are not much bothered with any kind of temporary load that is going to come on the structures like earthquake load, let's say wind load. No, we are much more bothered with the sustained load, permanent load that is going to be exerted on the structure, and these loads will be the cause of deformation, even if they are sustained with time, with the age of the structure in their service life. So, due to creep, the pre stress in tendons decreases with time because the tendons are embedded in the concrete, and by a strain compatibility, the creep strain in concrete will also cause equal amount of strain in steel tendons, and there will be pre-stress loss proportionately. So what are the different factors which affects the creep and shrinkage of concrete? So these are the different parameters and they are listed. First one is the age, and age is the most important criteria. Creep and shrinkage are mostly dependent on this age. And IS code IS 1343. Now 1343 is a prime number also. So you can remember this very special number. And IS 1343 takes into account of code of practice for pre-stress concrete basically. Okay, just like we use IS 456 for RCC. Okay, IS 1343 is dedicated for PSC. So IS 1343 consider only the age parameter in calculating creep and shrinkage basically. And then there are also different parameters like applied stress level, density of concrete, cement content in concrete, water cement ratio, relative humidity, and temperature. So these are different factors, okay, which are going to affect time dependent losses under creep and shrinkage. So for stress in concrete, less than one third of the characteristic strength. When stress in concrete, let's say FC is less than FCR divided by 3. Okay, for this value, the ultimate creep strain, this is the ultimate creep strain. We are talking of this value because ultimately there will be creep strain equal to ultimate creep strain E epsilon CR comma ultimate. Now this is in subscript. This is found to be proportional to the elastic strain in concrete. Okay, so ultimate creep strain is proportional to elastic strain in concrete. Okay, now this can be equated by introducing a parameter that is called theta, and the ratio of ultimate creep strain to the elastic strain is defined as this parameter, which is called ultimate creep coefficient. Ultimate creep coefficient, or we can simply call it as creep coefficient, no problem. So theta is our creep coefficient, and this formula is equally valid. Okay, this is epsilon CR is equal to theta times elastic strain in the concrete. So by this formula we will get the ultimate creep of strain in the concrete, and by a strain compatibility, the same ultimate creep strain will also come in the steel tendons. Okay, and that we have to multiply with the elastic modulus of a steel to get the loss of pre-stress due to creep. Okay, and as we have said that IS 1343 considers only the age of loading of the PSC in calculating ultimate creep strain. So age criteria is most important. That's why they are time dependent losses. So the loss in pre-stress delta FP, this loss is occurring in the tendons, steel bars. due to creep is given as follow. Now this is loss of pre-stress is equal to epsilon EP. Now this EP is the elastic modulus of pre-stressing steel is multiplied by epsilon CR ultimate, because this much ultimate creep strain was in concrete and will be in the steel also, because that's why the strain compatibility is valid there. Okay, strain compatibility. Now epsilon CR ultimate can be written as theta times elastic strain in concrete, and since this value we have used here. Okay, so this is how we calculate the loss of pre-stress in tendons due to creep. Okay, here EP is the elastic modulus of pre-stressing steels. Okay, curing the concrete adequately and delaying the application of external loads will surely provide long-term benefits with regard to durability, loss of pre-stress and deflection. So curing should be adequate and there must be delay in application of external loads. In a special situation, detailed calculation may be necessary to monitor creep strain with time. Some strain gauges has to be used in those cases if we have to get detailed analysis. Specialized literatures or standard codes can provide guidelines for such calculations. So as we have said that creep is only due to the sustained permanent loads only. Temporary loads are not considered in calculation of creep. Since the pre-stress may vary along the length of the member, now there can be parabolic curve. So pre-stress may vary along the length of the member. So which value we have to take? The average value of pre-stress is considered for calculating creep strain, losses in pre-stress due to creep. Next is the shrinkage of concrete. So shrinkage also occurs parallel with the creep in concrete, and there will be shrinkage strain in concrete, and by strain compatibility there will be equal amount of shrinkage strain in the steel also, pre-stressing steel also. So shrinkage, now time dependent strain measured in an unloaded and unrestrained specimen at a constant temperature, at room temperature, let's say. So this is the time dependent strain. Shrinkage occurs. Shrinkage is the time dependent strain, and here also loss of pre-stress delta FP in the pre-stressing steel due to shrinkage is given by a very simple formula. Again we are using almost same formula everywhere. Loss of pre-stress in steel tendons is equal to elastic modulus of steel tendons multiplied by the strain coming due to the shrinkage, epsilon SH. Epsilon SH is the shrinkage strain. EP is the elastic modulus of pre-stressing steels. So as per the IS 1343, the approximate value of shrinkage strain in case of design is given by these two formulas. Okay, first one is a constant value for pre-tensioning system of pre-stressing. If we are doing pre-tensioning, then epsilon SH is a constant and it is equal to 0.0003. Okay, but if we are doing post-tensioning system of pre-stressing, then epsilon SH is given by formula 0.0002 divided by log to the base 10 T plus 2. Here T is the age of concrete in days, not in months, weeks and years. Simple days. Okay, so this unit has to be used properly to get the shrinkage strain in post tensioning, and this we have to multiply here to get the loss of pre-stress in the tendons. So this was the time dependent loss due to creep and shrinkage in concrete, but there is another kind of time dependent loss due to deformation in steel also with time. So let's see that, and that is called relaxation. Relaxation means what? Relaxation is the reduction in stress with time at constant strain. So in this there is constant strain although, but relaxation is occurring. Relaxation is occurring means there is reduction in stress is occurring. and this reduction in stress is nothing but the loss of pre-stress in these tendons. So decrease in the stress is due to the fact that some of the initial elastic strain is transformed into inelastic strain under constant strain. Okay, some elastic strain was converted into inelastic strain, and here stress decreases according to the remaining elastic strain. And what are the different factors which is affecting relaxation? They are the time, initial stress, temperature, type of steel. So IS code gives a table here which shows how much relaxation loss is occurring in megapascal if we are applying initial stress equal to half of the ultimate strength of the steel. Then there is relaxation loss equal to 0, and as we go on increasing more than the 50% of the ultimate value, the relaxation losses also increases correspondingly. Okay, so that's why the relaxation depends on the initial stress. So initial stress should always be less. Okay, it should be loaded slowly. Okay, loading should be delayed after proper hardening and gaining strength. So relaxation loss can be calculated according to the IS 1343-1980 code, and this amount of loss is basically given most of the time, like this table is giving, and we can do sometimes interpolation also. So relaxation loss is basically calculated not much analytically but given directly in the case as is this table is given, and we can calculate the relaxation loss using this table by interpolation also. Okay, let's talk of the total loss which is allowed for in the design of pre-stress concrete. So there is always some amount of loss, and if we take a cumulative loss, that is called the total loss. So total loss is expressed as a percentage of initial stress which was provided in the design. And although it is very difficult to generalize the exact amount of total loss, however typical values are outlined, and this is given in the table of IS 1343, and type of losses are listed here: elastic shortening and bending of concrete, creep of concrete, shrinkage of concrete, creep in steel. So in case of pre-tensioning and post-tensioning, both of the values are given. Now you can see creep in steel is same as relaxation. So relaxation value is same in both of the cases. Okay, similar goes with the shrinkage of concrete, and creep of concrete is little more in pre-tensioning, because we do here pre-tensioning, because concreting is done after pre-tensioning, so that's why their loss is more. Whereas in case of post-tensioning it is a bit less, because we have already hardened the concrete. Now elastic shortening here is more pre-tensioning, and post-tensioning it is less, as we have discussed also. Because of subsequent loading, sometimes little loss occurs. Now if we take a sum of all, it comes out to be 25% in case of pre-tensioning and 20% in case of post-tensioning. You see this value? So this much total loss is allowed. Now why in the post-tensioning the loss percentage is less here? Because there can be some additional loss like anchorage slip, frictional loss, etc. But many a time anchorage slip is accounted by providing a slip length little bit, and frictional loss, although it can be there. So we can say that 25% is allowed in pre-tensioning and 20% is allowed in post-tensioning. So a reduction factor is also introduced in case of total loss allowed in the design, and here it is denoted as reduction factor is denoted by eta, and eta is equal to FPE divided by FPI. Now eta is the reduction factor for loss of pre-stress, and FPE is the effective stress in tendons after all the losses has occurred. Now FPI is the stress in tendons just at transfer at initial stage, and you take the ratio, it comes out to be FPE by FPI. Now the value of eta is generally taken as 0.75 for pre-tensioning and 0.80 for post-tensioning members. Now why 0.75? Because in post-tensioning we have seen there is 25% allowed loss, so that's why it is 0.75 eta value. Similarly, in case of post tensioning, 20% loss, total loss is allowed, so that's why the value of eta comes out here at 0.80. So this is all about the time dependent losses, and we will be discussing several numericals on time dependent losses as well as short term losses also in the upcoming videos. So till that, stay tuned and stay safe. Thank you.